Good morning, calculus students. Today's lesson is going to focus on the title right here, how to sketch the derivative of a function given the graph of a function. So we've been finding a lot of derivatives. Now we're going to learn how to sketch them given the original graph. So the directions here say, for each example below, analyze the slopes of the tangent lines on the graph of f of x. Use these slopes to sketch the derivative of f of x. Okay, so we're going to tackle example 1, and I'm probably going to go the slowest through this example because once you learn sort of my technique for doing these graphs, it applies throughout. So I'll really take my time here on example 1. Okay, so let's think about example 1. Here we have x and we have y, or we could say f of x, y or f of x. All right. Now you have learned since way back, middle school, maybe even elementary school, that on a coordinate plane, when you have a graph, so we have this graph here of this linear function, every ordered pair can be written as such. Like, for example, you have 0, 0. So the point 0, 0 is on your graph here. And that's an x and a y, or an f of x. If you look here, the point 1, 1 is on your graph. That's x, that's f of x. And then the point 2, 2 is on your graph. So these are just x's and y's that take us to the location on the coordinate plane where the points fall. This is how we've always learned how to read ordered pairs. Okay, well today we're going to be graphing f of x's derivative. So this is going to be a little strange at first. The x-axis is still going to be the x-axis, but the y-axis is no longer going to be the y-axis. It's going to be the derivative axis. Now this notation is going to look a little new because we've been learning that the notation for derivative is slope of the tangent at a point x f of x. Today I'm going to introduce a shorter way of saying slope of the tangent. So we have the x-axis, now we have the derivative axis, and we're going to call the derivative axis f prime of x. This notation, f with this little mark here, it looks like a 1, it's called f prime of x. F prime of x means the same as slope of the tangent line. Okay, so this is the derivative. Both of these mean derivative. So the y-axis no longer represents y coordinates on this graph. The y-axis represents, get ready for it, the slopes of the tangent lines on this graph. Okay, so as we're going out 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, we're going to be calculating the slopes of this graph, and that's what the f prime values will represent. So what I like to do when I'm first teaching this is make a table in between the two graphs. So I'm going to call this table x, f prime of x. And remember, for every x value we choose back here, we're going to be looking at the slopes of the tangent lines and putting that number, whatever the slope is, in this column. We'll then be plotting these points over here and we'll have the derivative graph. So what I like to do is I'll pick a negative, I like to pick the origin, and then I like to pick a positive value. So I kind of have a nice representation, negative, 0, and positive on my x-axis. So maybe I'll pick something like negative 2 here. So let's choose negative 2, and then I'll choose the origin, 0, and then I'll choose positive 2. Okay, so let's go over to negative 2. Okay, so x is negative 2. What you want to do is come down here to the graph. So you are at the coordinates, and I put the coordinates over here. So the coordinates are negative 2, negative 2. That's your x and your f of x, like you've always learned. But now what we're going to do, when you get there, I want you to draw a tangent line. Now, because it's linear, the tangent line is going to lie right on top of the original line. And the slope there, well, if we calculate the slope of this linear function, it looks like I'm going up one, right one, up one, right one. So I'm going to say that the overall slope of this entire line is m equals 1. So at -2, -2, my slope is 1. Okay, let's go to 0. So when x is 0, okay, I'm right here. Draw a tangent line. Boom. Again, it lies right on top of the line, so the slope at 0 is 1. And now I go to 2, 2, 2, which I had marked over here, 2, 2. Draw a tangent line. Boom. The slope is 1. Okay, so let's go to our derivative graph then. So if I plot the point -2, 1, -2, 1, 0, 1, and 2, 1, and I connect those dots, I've just graphed my derivative. So the derivative of this linear function looks like this. Now here's what's going to get really interesting by the time we get to tomorrow's lesson. In tomorrow's lesson, we are going to learn some shortcut rules to finding derivatives so that we don't always have to go through the limit as h approaches 0 of f of x plus h minus f of x all over h. And what mathematicians started to put together are things like what I'm about to show you. So take a look here. If I wrote the equation of this line back from Algebra 1, so if I wrote y equals mx plus b, the slope, we already realized the slope is 1, so I would do y equals 1x, and then my b is 0 because I'm crossing the y-axis at 0. So this is my original equation. Now, if you look over here at the equation of my derivative, this is a horizontal line at y equals 1. So the derivative equation is y equals 1. And one of the shortcuts we're going to learn tomorrow is that the derivative of any linear function is just the slope of that function, because the slope is unchanging the whole way throughout the domain from -infinity to +infinity. And so this is showing that the slopes are steady at 1. So we know that linear turns into horizontal, and it is whatever the slope of the function is. Okay, so let's look at example 2. Example 2, we've got ourselves another linear function. So again, we have, actually, they mark some points on here. Regular old x's and y's, regular old x's and y's. But what I want to do is make an f prime of x chart, and I want to look at what the slopes are actually doing. So if let's just use some of the points they marked here. So let's just go to -5. So if I go to -5, and I come up on the graph, and I draw a tangent line, the slope of that tangent line there is just the slope of this line. So if I kind of count my rise and my run here, from here to here, these two marked points, I'm coming down 2 and right 4. So down 2, right 4 is -0.5. Okay, then they have another marked point for me here at -1. So let's go to -1 on the x-axis. Draw a tangent line. It's right over top of the regular line. The slope there is also going to be -1/2. And then maybe I go over to a point that is over here, maybe like it looks to me like down to 1, 2, 3, 4, right here, when x is 3, if I draw a tangent line, slope is also going to be -1/2. Okay, so I go over to my graph. So I plot the point -5, -0.5. So 1, 2, 3, 4, 5. We'll call that -1, so -0.5 we'll put about right there. -1, -1/2. And then 3, 1, 2, 3, -1/2. So I've got this horizontal line at y equals negative 1/2. So this is x. This is that notation f prime of x representing the slopes of the tangent lines. So my derivative graph is y equals negative 1/2. That's the horizontal line there. This graph here, if I'm doing y equals mx plus b, I know that it's y equals negative 1/2 x plus b. Now, if I wanted to find the actual b, because I can't quite see it here, it's coming between 0 and negative 1, I could just plug this point in. X would be negative 1 and y would be 0. So 0 equals negative 1/2 times negative 1 plus b. And if that's a positive 1/2, so if I subtract it over, my b is going to be negative 1/2. Okay, so this equation is y equals negative 1/2 x minus 1/2. Now, the slope of this line is steady and unchanging at negative 1/2. So the derivative is just that slope, unchanging and steady at negative 1/2. Very cool. Okay, so this is going to be actually one of the shortcut rules that we learn tomorrow, is that the derivative of any linear function is just the slope of that function. So keep that in mind for tomorrow's lesson. Okay, flip it. Oh, check it out. Example 3, piecewise in 3 pieces. Piece number 1, piece number 2, piece number 3. So we're going to kind of use that linear idea again, but it's going to do some shifting as we move from left to right. So with this kind of a function, I mean, you can certainly make your tables like we did on the front, but with this one, it might be easier. Let me just set us up here. So we've got our x-axis here, and we've got our f prime of x axis here. Okay, and I'm just gonna put some marks here. Go out to -4, out to +4, maybe up to +4, and down to -4. Okay, so let's take a look at this first segment. Do you see how it's linear? Obviously. Let's catch the slope of this. So the slope of this line segment looks to me to be up 1, right 1, up 1, right 1, up 1, right 1. So I'm thinking a +1. Then it switches. Now check it out. At 1, 4, we have a visual cue here of non-differentiability. We have a corner. So we don't have a derivative at 1. But as we go from 1 to 2, uninclusive, the slope changes to, let's count the rise and the run here. From point to point, I'm going down 1, 2, 3, 4, 5, 6, and right 1. So that switches to -6. And then at 2, -2, I'm non-differentiable again. And my slope changes again to up 1, right 1, up 1, right 1. So back to +1. So without going through the whole table, we might be able to get this pretty easily. Here's how. Let's mark 1 and 2. Let's kind of highlight them. So at 1 and at 2, we have this sort of dramatic change in slope going on. We're also non-differentiable. So right here, we are non-differentiable, meaning we do not have a derivative. And also right here, non-differentiable. We can't draw a tangent line there. So we can't have a slope of a tangent line where we can't draw a tangent line. The slopes from the left and the right are fighting each other. So we'll call that non-differentiable. Okay, so we have a steady slope of +1 from -infinity up to, but not including 1. Okay, +1 slopes up to 1, but not including 1. So at -5, or let me do -4 because that's how far I went. So at -4, slope is 1. See how I'm at -4, 1? At -3, slope is 1. -3, 1. At -2, slope is 1. -2, 1. At -1, slope is 1. At 0, slope is 1. But at 1, I can't draw a tangent line there because it's fighting with this tangent line. So I just say non-differentiable, so I just open that circle. Okay, now between 1 and 2, everywhere between 1 and 2, my slope is steady at -6. So 1, 2, 3, 4, let me come down here, 5, 6. So between 1 and 2, my slopes are -6, but at 1 I'm non-differentiable, and at 2 I'm non-differentiable. So I'm going to open those holes. Okay, from 2 to infinity, uninclusive on the 2, my slopes are back to +1. So I'm going to come up to, oh, wrong one, I'm going to come up here, and all these slopes to the right are +1. That's what you're showing there. You're showing that your slopes are +1 forevermore this way. Your slopes are +1 forevermore that way. And they jump to slopes of -6 between 1 and 2. So that's what that looks like. Okay, now in example 4, we're getting into some quadratics now. Now I will tell you, for those of you who like to be exact, you got to kind of let go of that on this right here, because we're just sketching for right now. So here we have this quadratic function. Okay, so I'm going to kind of go back to the table idea. So we're going to take x, f of x, and we're going to turn it into x, f prime of x. And to do that, I'm going to make a table, x, f prime of x. And I'm going to pick some x's and analyze the slopes of the tangent lines. So let's choose a negative, let's choose the origin, and let's choose a positive. So I might choose -2, 0, and +2, just like we did on that first example. So let me go to -2. Okay, -2, come up to the graph, about right here, and let me draw a tangent line. So there's my tangent line. Now let's talk about the slope of this line. The slope of this line, I'm not exactly sure of the numerical value, but I know it's negative. I know the slope is negative. So what I'm going to do here in my chart is when x is -2, I know the slope of the tangent line is some negative number, kind of steep. When I go to 0, let's go to 0, 0, the vertex. We know that from the left and the right, these slopes are approaching horizontal 0, so I'm going to draw a horizontal tangent line there. And the slope here is going to be 0. Okay, so 0, 0. And then at 2, let's go to 2, come up on the graph, draw a tangent line. This is going to be a positive slope. We don't know exactly what positive, but we know it is positive. So at 2, my slope is positive. Now this is where my very particular students have a little trouble because they want the exact numbers, but you're not going to have them right now. All you can do on this derivative graph is go to x equals -2 and drop down for your f prime value to some negative. I'm not even going to mark it. I don't know how negative. I just know it's negative. We're just sketching. 0, 0. There you go. That's a point to plot. And then 2 positive. So 1, 2, and a positive. Okay? You connect those dots, and you've got yourself a linear function. Now tomorrow we're going to learn when we do shortcuts, like if this right here is the graph of y equals x squared, tomorrow we're going to learn a shortcut called the power rule, which tells us that the derivative of x squared is 2x. Now you don't know why, I mean, you don't quite get that yet, but if you look at this and this, because I know the derivative, quadratics go to linear. Quadratics go to linear. And if you want to know the rule right now, what you do is you just bring this exponent down to the front and reduce that exponent by 1. So it becomes 2x to the first power. So quadratics become linear. Everybody steps down 1 degree when you're doing derivatives. You'll see that in our shortcuts tomorrow. Okay, example 5. Now you're getting the gist here. So for example 5, I'm going to go a little bit quicker. So if I'm graphing x and f prime of x, what you can see here is that as I'm doing my table, if I go maybe to -1 here, so at -1, I'm like right here, if I draw tangent line. It's positive. Don't know what positive, but I know it's positive. If I go to 0, it looks like I'm still positive. I'm just a little less positive. I'm a little less steep. See how the steepness declined? If I go to 1, boy, I sure hope that's a 1. It's hard to see. We'll say that that's 1. I'm with a slope of 0, so 1, 0. And then at 2, I'm negative, so 2, negative. And then at 3, I'm still negative, but more negative. More negative. So let's take a look at what this might look like here on the derivative graph. So -1, positive. So -1, positive. 0, less positive. 1, 0, okay. 2, negative. And 3, more negative. Linear. So my quadratic went to linear. But notice the difference between here and here. Here my slopes went -0, positive. So -0, positive. Here my slopes went +0, negative. So it switched the way my line is sloping. Okay. 2 more examples. What I'm actually going to have you do is pause the video and try these. See what you can do with it, and then replay it and see if you match me, okay? All right, so hopefully you pause the video and we're back. Going to do 2 graphs here. And I'm going to see if I can do them without the tables. Hopefully you made the tables. I'm going to try to do it without it. So if I choose something like -2 here, the slope is positive. So -2, positive. And then I choose -1. It's positive, but less positive. At 0, it looks like my tangent line would have a slope of 0. At 1, just barely steep, positive, not steep at all. And at 2, positive, but steeper slope. Check it out. My cubic just became quadratic. 1 degree down, cubic to quadratic. Very interesting. This is another cubic here. So this should also turn out quadratic. So let's check it out. If I go to, let's go to -2. So if I go to -2 right here, slope, positive. If I go to -1, slope, 0. If I go to the origin, slope, negative. If I go to 1, slope, 0. And if I go to 2, slope, positive. That's 2. So you can see, also quadratic, cubic to quadratic. Very cool. So my slopes go positive, 0, negative, 0, positive. Positive, 0, negative, 0, positive. So hopefully this video made sense. This is how you sketch a derivative graph from an original graph. And I'll see you on the next video.